that will not help.
You sure?
Pretty sure, baby love.
I'm gonna calculate this as.
Sweetheart, I'm starting class. I'm gonna close this door. I love you. It's strange. Only 6 of us. Well, 6 of us, me included, so 5 of us. All right, I'll give a minute here because I actually need to talk to you guys for a second this morning. I do want to use our class time well. We do have quite a bit to do today. So I'm gonna go ahead and flip over the doc cam and start with announcements and stuff like that. But of course, I need people to be here to talk to them. So hopefully. Let's get this camera connected. Unfortunately, I can't wait and burn more class time, hoping that folks who need to hear this show up. So if you put forth an honest effort on exam 1 and whether it went well or not, I'm proud of you. That's a good thing. Even if it didn't go well, what I'm about to say is not to you. I've been teaching for a pretty long time, right? I taught at UCF and at UF and here at Santa Fe. I've done online classes, hybrid classes, lab classes, all sorts of different things. And I have never in my life seen as much cheating on an exam as I saw in this class's exam 1. Unfortunately, the drawing pad that I was using to grade doesn't work well. So I'm really not able to give the level and intensity of feedback that is called for here. But suffice it to say that when you do something for a long time, you develop a pretty good feel for it. And it's not hard to see when someone does and doesn't have a strong grasp of the material. And it's not hard to see when someone isn't showing their own work. There are some steps that I can do in my head. There are some steps that I know you guys can do in your head. And there are some things that I know nobody can do in their head. Even Srinivasa Ramanujan or Frank Garvin or Paul Erdős wouldn't do 2 runs of integration by parts without writing a single fucking thing down. So again, if you put forth your best effort on this test, then whether it went well or didn't go well, I'm proud of you. No matter what you did, because this is the first test, there's room to turn it around. If you cheated on this test, I know. It's not hard to tell. I don't enjoy conduct trials. I do my very best to avoid them. I like to work around, talk to students, try to come to a place where we can move beyond that shit. But like I said, I've never seen cheating like I saw in this test. And beyond the personal frustration that I feel, it's really harmful to your everything, to your character, to your development as a person, but most importantly to me, to your development as a mathematics student. You can't cheat your way through this class. If you thought it was a little bit tricky to cheat on the first test, wait till you see the second. because the second test is all proof writing. There's literally no way to do it. You can cheat to get the result, but you'll never be able to structure the problems. You'll never be able to write the solutions without actually understanding the material. That's a little bit true of the first test, but it's very, very much true of the second test. So I want to just put this out there. If you cheated on this first test, I probably called you out for it a little bit in the comments. Read the comments on the exams, right? So there's 2 places you can go to read comments. Written comments are on your free response work, and then there are some typed comments on the problems in the exam itself. So go to both places to read comments. If you cheated on this test, please read the comments and don't do it again. I made some very explicit and very clear warnings in those comments, and I will 100% follow through with those. Dan Rodkin's a good buddy of mine, and that's it, right? That's all. Just don't do that shit again, okay? I know not everybody did. I know some people, despite the temptation, which I'm sure was really extreme, despite knowing that the test was not going as well as it could have for them, some people were exceptionally brave and just wrote down what they knew. And I have huge respect for you guys who did that. That's exactly what you should do. I know it's hard to do that in that situation, and I'm really proud of you. And when I see that, I do everything I can to find all of the partial credit that I can in your work. But again, to those who cheated, and I know there's a lot of you, don't fucking do that again. If I see it again, it's a ZF in the class. And that's not just going to be the end of this class. That's going to be the end of any hopes for transfer, really. Because if you have a ZF on your transcript, nobody's going to take you. So this is your one and only one warning. All right, is that clear? I don't like this shit. I don't want to have to deal with it like that. I understand that this environment is new and the temptation is overwhelming, but you need to be stronger than that. So let's be stronger than that moving forwards. All right, that's enough of that shit. So let's get back to talking what we were talking about. We were talking about sequences. Last time we introduced the definition of a sequence. We talked about pattern finding. We talked a little bit about notation. Today, I want to talk about limits of sequences and convergence. So, we have a notion of convergence for improper integrals. That's our first notion of convergence, and you have a few theorems relating to the convergence of improper integrals, and hopefully that now is in your notes in a special safe place where you can refer back to them. Today we're going to get our second notion of convergence. So just like improper integrals can converge or diverge, sequences can converge or diverge. But for a sequence to converge or diverge means something very, very different, because as objects, they are very, very different than improper integrals. Before we talk about that, I guess I want to talk about graphs. Graphs of sequences. And then we'll develop a few theorems. So let's actually talk about the graphs first. And I'd like to do this through an example. One of the examples that I think we looked at last time was the sequence AN defined by the rule AN equals 1 over n. So the nth term of the sequence is the reciprocal of the nth positive integer. And here, of course, n starts at 1. You can graph such an object, just like you can graph any other function, right? If you have any function with a one-dimensional input and one-dimensional output, you can graph it. Well, we're used to graphs of functions being curves or segments of curves, things like that. The graph of a sequence is a little bit different. Still, the horizontal axis is our input space. So this is the n axis. And the vertical axis is our output space. So I would label this as y equals an. A1 is 1, and so the point 1, 1 is on the graph. Right? The first term, A1 here, is 1. Now remember how we read this? You can call it A of 1 or A sub 1, but not A to the 1, because that's confusing. So I'll just call this A1. A1 is equal to 1 over 1, which is 1. A2 is equal to 1 over 2, which is 1/2. So the points 1, 1 and 1, 1/2, 2, 1/2 are on the graph. And you continue in the natural way, right? A2 was 1/2. A3 is 1/3. So the point 3, 1/3 is going to be on this graph. A4 is 1/4. So the point 4, 1/4 is going to be on the graph. And 5, 1/5 will be here as well. And of course, this goes on and on and on forever and ever and ever, just like the graph of a function, right? Just like the graph of a continuous function. In fact, these points all live on the graph of a continuous function that you guys know and know well. So the first kind of note here, the graph of a sequence is a collection of dots. If you think about it from the perspective of the second definition that we gave on Monday, a sequence is a function whose domain is the natural numbers, right? So if you smush all these points down onto the x-axis, you shouldn't get all of the x-axis or onto the horizontal axis. You should just land on the whole numbers. And that's the case here, right? The domain, the set of all x values actually on the graph, or the set of all inputs actually on the graph, is just 1, 2, 3, 4, 5. There's like nothing in between here on the graph of the sequence. So this is the graph of the sequence 1 over n. But the second thing I wanted to mention is that these points do all live along a curve that you guys should know pretty well. So here, let me see, where can I do this? This is the graph of 1 over x. And you notice that the graph of this sequence is just a bunch of points along the graph of 1 over x. So another note, not every sequence is like this. Some sequences, like this one, can be thought of as the restriction of a continuous function to the natural numbers. And sometimes that's a very powerful observation, specifically when it comes to doing the thing that we're going to start doing today, which is taking limits. One asks a good question in chat. If I ask you to graph a sequence, should you draw the line connecting them? No. And that's why I've put that in here in a different color. The blue here is not a part of the graph of the sequence. The graph of the sequence is just the dark red. Okay, is that clear? The blue here is not a part of the graph of the sequence. The graph of the sequence is just the dots. The reason I've drawn the blue in here is to illustrate this second note. That many sequences, especially the sequences that we're going to play with in this class, many of the sequences that you'll encounter can be thought of as dots along a continuous graph that you already know. So if I ask you to graph the sequence n squared, for example, you know what the graph y equals x squared looks like. You would just need to put some dots in place, along that graph, and those dots would be the graph of your sequence, right? If I asked you to graph the natural log of n, you know what the natural log of x looks like, so you could sketch that curve and then put dots there at the integer inputs. Those dots would be the graph of your sequence. The main reason this is useful is because the dots are restricted to this curve, which means if you can find the limit of the curve, you can find the limit of the dots. And limits are kind of one of the main things we're going to be talking about when it comes to sequences, but I'm getting ahead of myself. So the point here is just that, yeah, the red is the graph of the sequence. Don't worry about the blue. The blue is not a part of the graph of the sequence. But sometimes we can think of sequences as living along these curves. So I want to look at one more graph of a sequence to illustrate that not every sequence can be thought of this way, at least not in any natural way. Many applications, many applications for sequences, especially in computer science, right? If you think about writing a computer program, if you've ever done that, every time you write a for loop or a while loop, you're encoding a sequence of actions. But not just there, many other places also. Me as a mathematician, I'm not particularly interested in the applications, but yes, there are lots and lots of them. Queuing theory in discrete mathematics, we study objects that are not necessarily continuous in nature. And there are lots and lots of applications in the medical field. I think the famous one that I've heard about most recently on the news was the problem of loading passengers into an airplane, right? What's the most efficient way to load passengers into an airplane? This is a sequence of actions, right? You're associating to each seat on the plane a person, and you're doing it in a particular order. So there's a first passenger, a second passenger, a third passenger. Yeah, there is. There's a handful of them. And so queuing theory is all about studying sequences, but that's just one of many applications. So let's sketch the graph of the sequence defined by the rule an equals -1 to the n, where n is 0, 1, 2. Computer networking and telecommunications, also an area where sequences and graph theory especially are hugely important. The traveling salesman problem you may have heard of, another application of sequences. Okay, so suppose this was a question on a test. What do we do? How do we graph the sequence -1 to the n? Yeah, we'll start with some coordinate axes. Here I know that the outputs for this sequence, remember we looked at this one on Monday, are just -1 and +1. So on my vertical axis, I only need to label those two numbers. And on my horizontal axis, I know I'm only worried about whole number inputs. So I'll just tick off a few here. And then I ask myself, okay, well, what's the first output? What is A0? So remember here, I'm starting at n equals 0. A0 is -1 to the 0th power. That's +1. And that tells me at the point 0, 1 is on the graph, just like it would if I was graphing any other sort of function. A1 is -1 to the 1, which is -1. In other words, we kind of approach this the way you would in like 8th grade when you first learn how to graph functions. We're just going to plug in some inputs and see what outputs we get. A2 is -1 to the 2, -1 squared, which is +1, so we're back up here. A3 is -1 to the 3, that's -1, so that brings us back down here. And by now we can spot a pattern, right? You notice that at all the even inputs, this thing is outputting +1, and at all the odd inputs, this thing is outputting -1. So without computation, I know that 4, 1 and 6, 1 are on the graph, and I also know that 5, -1 is on the graph. And if I wanted to, I could say, okay, 7, -1 is also on the graph. So what you notice here is that this doesn't necessarily look like dots along the graph of any continuous curve. Indeed, if you try to form the function -1 to the x, that's a horribly behaved function. And you plug in 1/2 to that, then you get I. All sorts of weird shit going on. So this one, you're not going to find like a blue curve you can draw in here so readily. Yeah, you could sneak around with some cosine stuff, and we saw that last time, right? -1 to the n can also be thought of as cosine n pi. So if you drew the graph cosine pi x, you could actually make that work here. But that's a subtle and tricky thing. So the point is that swapping the n for an x does not always give you the blue curve like it did in the last example, right? Here we got the blue curve by saying, okay, 1 over n, that's got to be points along the graph of 1 over x, right? You just swap the n for an x. Down here, if you do that, the function you get is not at all nice. There's a reason you've never seen an exponential function with a negative base. It's because they're horribly, horribly behaved. Okay, so that's how you graph sequences. The notion of convergence for a sequence. This is our second notion of convergence. Here we're going to use the word converge, but it's going to mean something very different than it meant when we were talking about improper integrals. It's still the same general idea that an infinite process leads to a finite result. We say the sequence an, and if I want to refer to the sequence as a singular object rather than as the nth term, like all the terms together, I put an in curly braces. We say that the sequence an converges if the limit as n goes to infinity of an exists and is finite. If lim n to infinity an does not exist, or is not finite, then we say the sequence an diverges. Okay. So this is the concept of convergence for a sequence. And in order to really wrap our heads around it, we need to know what it means for the limit as n goes to infinity of an to exist. We need to understand what it means to take a limit of a sequence. The intuitive definition for the limit of a sequence is what you think it is. It's really the same as the definition for the limit of a function, because sequences are functions. The limit as n goes to infinity of an exists and is equal to some number L means as little n gets bigger and bigger, the output an gets closer and closer to L and stays close to L. So this is an intuitive definition. It's not rigorous, but it is the way that we usually think about things. I want to draw for you a picture here that makes it a little bit more specific. In fact, I'll go ahead and give you the grown-up definition. Lim n to infinity an equals L means for any epsilon greater than 0, there is a number capital N such that the absolute value of an minus L is less than epsilon whenever little n is bigger than capital N. So the first definition is intuitive. It works very good just for thinking about things, looking at pictures, coming up with ideas. The second definition is the sort of thing you would use to prove a sequence converges. I won't make you work directly with the second definition. Instead, I will give you some theorems that you can use, because this second definition is a little bit hard to work with if you're not used to working with epsilonic analysis. But there is a picture I can draw for you that will help you understand both definitions. The first man to really codify these ideas was Augustus Louis Cauchy back in the 18th century, around the time of the American Revolution. And so sequences that do this thing where they get closer and closer and closer to something are called Cauchy sequences in his honor. Here's the picture. I have some sequence an, and maybe it starts off doing all sorts of weird shit. I'm not sure. But if you give yourself a little epsilon window, meaning You go up from L by epsilon. You go down from L by epsilon. And you look at this kind of horizontal window that creates. Then eventually there is some number capital N so let me also bring L through here. Eventually, there is some number N such that my sequence gets trapped in this window and it never ever emerges. And you can shrink this window down. And as you go further and further, N might increase. So maybe here's cap N minus 1. Maybe we're outside the window there. But you can make epsilon as small as you want. You can shrink this window down, and still the sequence will be trapped in there from some point on. That's the idea. I know this might be a little bit hard to wrap your head around. There's a few ways to characterize this. You can say all but finitely many terms of the sequence are within epsilon of L, no matter how small epsilon is. That's one way to say it. Or the terms of the sequence get close and stay close to L, getting closer and closer as N gets bigger and bigger. In other words, it's the same definition you used for limits at infinity with continuous functions. It really is. So you may go back and look at section 2.6 in the textbook, remind yourself how limits at infinity worked there. But it really is the same definition. And the good news is that all the tricks you learned back in Calc 1 for limits at infinity, for the most part, work great here with sequences. Yeah, L is the limit of the sequence. So usually your goal is to find L. So certainly it varies from problem to problem. So for example, if we revisit the sequence we started with and try to find the limit as n goes to infinity for the sequence an equals 1 over n, everybody has some basic idea here. Just like 1 over x goes to 0 as x goes to infinity, 1 over n will go to 0 as n goes to infinity. But to help you see it in view of this picture, in the context of this picture, we can graph that sequence again. A1 is 1, A2 is 1/2, A3 is 1/3, A4 is 1/4, A5 is 1/5. And no matter how big I pick epsilon, so here L is equal to 0, so this would be epsilon, and down here would be negative epsilon. Let me use blue for my epsilon window. So here I've drawn epsilon to be about 1/4. And you see that once we are beyond n equals 4, the terms of the sequence are all trapped inside this window. And indeed, if I were to shrink the window, you would still have all but finitely many terms trapped inside. And the terms are getting closer and closer and closer to 0. So once you enter this window, you're trapped in that window. And as you go further and further and further to the right, your dots are getting closer and closer and closer to 0. So the limit as n goes to infinity of 1 over n is 0. Again, you're not responsible for the epsilon definition. Like I said, I'm going to give you some theorems that will allow you to work through these problems like you did in Calc 1 when you were taking limits at infinity there. But I would like you to think about this definition, because really in mathematics, everything is built on sequences. The real numbers themselves are constructed by thinking about sequences. Intuitively, if I said the limit as n goes to infinity of 1 over n is 0, everybody kind of understands that, right? If you put in a huge number for n, 1 over n is going to be very, very small. And if you send n to infinity, 1 over infinity, that should be 0. If it's going to be anything, it should be 0, right? Because 1 over bigger and bigger and bigger numbers gets closer and closer and closer to 0. That's the level on which I need you to understand it. So again, you're not responsible for the epsilon thing, but thinking about the epsilon thing is a healthy thing to do. It'll be good for you. So I'd like to give you the first of our theorems now. The first theorem allows you to take everything you know from Calc 1, limits at infinity, and move it into the sequence domain. This says if an is the same as f of n, where f of x has lim x to infinity, f of x equal to L, then lim n to infinity, an equals L also. So if your sequence is dots along some continuous function that you know has limit L, then your sequence goes to L also. The picture here like this. So if you know that this blue curve is going to have limit as x goes to infinity being L, then any sequence that is trapped along that blue curve has to go to L as well. So the blue curve here is f of x. And what you're seeing here is that a1 is the same as f of 1. a2 is the same as f of 2. a3 is the same as f of 3. In general, my sequence here is coming from values of this continuous function. Since the continuous function goes to L as x goes to infinity, the sequence an goes to L as x goes to infinity as well. The sequence is trapped on the function. So wherever the function goes, the sequence goes also. A lemma, a consequence of this, I shouldn't call it a lemma, corollary, we know that for any positive number p, that the limit as x goes to infinity of 1 over x to the p is 0. Hence, for any positive number p, we have limit n to infinity 1 over n to the p equals 0 also. So 1 over n squared, 1 over n cubed, 1 over the square root of n, all of those sequences go to 0. So what this says is that all the stuff you learned about limits at infinity in Calc 1 can be moved into the domain of sequences. That's all. That's what this says. In other words, if when you swap n with x, you know how to take the limit, you can use those tricks here. An example, let's say I want to investigate the convergence of the sequence an equals the inverse tangent of n. Okay, I would say, well, we know that lim x to infinity inverse tangent of x is pi over 2. Since an is equal to inverse tangent of n, lim n to infinity an must be equal to pi over 2 also. Right? Does this make sense? Here my sequence is arctan 1, arctan 2, arctan 3, arctan 4, arctan 5. Those are all points along the graph of arctan x. Since arctan x goes to pi over 2 as x goes to infinity, arctan n has to go to pi over 2 also, i.e. the limit as n goes to infinity of arctangent of n is pi over 2. So we say the sequence an equals inverse tangent of n converges to the value pi over 2. I'd like to take a second and pause here to answer any questions on this example or on this corollary or corollary, if you're American. Questions on those guys? Another way to write this, if you didn't want to be so wordy about it, would be to just say lim n to infinity inverse tangent of n equals lim x to infinity inverse tangent of x equals pi over 2. So the sequence an equals inverse tangent of n converges to pi over 2. Right, if you want a more succinct way of writing it. I'm using the theorem here when I say that the limit as n goes to infinity of arctan n is equal to the limit as x goes to infinity of arctan x. That's where I'm using this theorem. Now, I would like you to be comfortable with the kind of wordier solution there, because it kind of demonstrates an understanding of the theorem. But really all we're doing when we use that theorem is swapping n for x and then using whatever tricks we know about taking limits of functions. Let's do one more like this. 1 minus e to the negative n. Well, here, 1 minus e to the negative x, that's a function I should know pretty well. So I could say lim n to infinity of 1 minus e to the negative n is equal to lim x to infinity 1 minus e to the negative x. And then here, this e to the negative x piece, that's 1 minus 1 over e to the x. So I know that this is 1 minus 1 over infinity. And since 1 over infinity is 0, this is just 1. Thus, the sequence an equals 1 minus e to the negative n converges to 1. Questions on any of these last few examples? All right. Let's look at the convergence question. For the sequence -1 to the n. Here, like we said, I can't just swap the n for an x because that is not a well-behaved function. But I can look at the graph. I've already graphed this once, so I'm not going to spend a lot of time on it. What do you guys think here? Yeah, good. So here, there is no number L that these dots are getting closer and closer and closer to, is there? You might think, oh, maybe L equals 1 works. Maybe the sequence is converging to 1. But then if you take an epsilon window and you put it around 1, there's no way to force the sequence to get in there and stay in there. No matter how far out you look, you're not going to get close to and stay close to 1. And the same is true for -1. So here the limit as n goes to infinity of an, what's the limit as n goes to infinity of -1 to the n? This does not exist. Similar to like lim x to infinity sine x not existing. Yeah, because it oscillates. Now, sometimes oscillating isn't the end of the world as long as you oscillate and like that oscillation closes in. But here, that oscillation does not close in. So yeah. So this sequence, an equals -1 to the n, diverges. Okay, there's one other really important trick before I get to introducing more theorems. This is a trick called, I call it renormalization. This is useful for limits of rational sequences. Here, if I just try to like plug in infinity, the top and bottom both go to infinity. Not helpful. So your first thought might be L'Hopital's rule. And L'Hopital's rule can be used, right? Because I can here swap the n's for x's, and then in that limit involving x's, apply L'Hopital's rule. That's an option, but it sucks. It sucks because you got to differentiate a few times to make it go. It sucks because the square root of n derivative, the square root of x derivative isn't super nice. What's much nicer is this renormalization trick, where you divide top and bottom by the largest power of n found anywhere. So the largest power of n I see anywhere here is n cubed. So I'll divide top and bottom by n cubed. This is a nice trick, and most people learn this in Calc 1 when they talk about limits at infinity. I just want to remind you how the trick works, because it works really well in the setting of sequences also. If I distribute this 1 over n cubed in the numerator, 1 over n cubed times n cubed is 1, minus 2n squared over n cubed is 2 over n, plus root n over n cubed is 1 over n to the, 2.5, which is 5 halves. Downstairs here, 5n cubed times 1 over n cubed is 5. And 2n divided by n cubed is 2 over n squared. And now, as I send n to infinity, I have 1 minus this piece goes to 0, plus this piece goes to 0 over 5 plus this piece goes to 0. Because remember, lim n to infinity 1 over n to the p is 0 if p is positive. So this is 1/5. This trick of dividing top and bottom by the largest power of n is a really, really, really nice trick. If there's one important trick for calculating limits at infinity, it's this. All right, there's lots of tricks. I'm going to show you lots and lots of tricks, but this is the most important one. Is anybody seeing this for the first time? Anybody's Calc 1 class not cover this when you talked about limits at infinity? I know not every Calc 1 class does. Okay, so I want to be respectful of your time. What are we doing? 9:04. All right. There are a handful of other theorems from this section. Before I show you the remainder of the theorems, I want to introduce a new kind of sequence. So some sequences you're given just a formula, right? AN equals some formula involving n. Those are relatively easy to work with as long as the formula isn't unmanageable. But there's a whole other family of sequences. It's a whole different way that you can define sequences. And these are called recursive sequences. And those of you interested in applications will find a home here. Recursive sequences are like the sequence version of differential equations, if you've ever heard of differential equations. Maxwell's equations, for example, in physics are differential equations. When you want to describe a phenomena in the real world that changes over time, like you have a system that evolves over time, the natural language for doing that is differential equations. If you want to describe a system that evolves through steps, then the natural language for doing that is the discrete version of a differential equation, which is called a difference equation. And those are just another name for recursive sequences. The famous example I'm supposed to show you now is the Fibonacci sequence, but there's a more important one. You ever tried to count the number of ways you can do something? Like the number of ways I could pick 2 people from this class to like form groups of 2. Yeah, like how many ways could I form you guys into groups of 2 if we wanted to go into breakout rooms right now? Or how many ways can you seat people at a dinner table? If you have 5 people, 10 people, how many ways can you seat them at a dinner table? The function that's primarily involved in calculations like those is a recursive sequence. So these are sequences where I tell you the first few terms, and then tell you how to get the next term as a combination of the previous terms. So the first term, or the first few terms, those are called the initial conditions. And the rule that tells you how to get the next term from the previous terms are called the recurrence relation. I will do the Fibonacci thing, but before that, there's a more important one. I'm going to call this sequence capital F sub n. And I'm going to tell you, so the sequence capital F sub n, referring to it as a singular object, so I put it in braces, is defined by the rules capital F sub 0 is 1, the first term, or the 0th term, the starting term. and fn plus 1 is equal to n plus 1 times fn. So this is your initial condition. And this is your recurrence relation. Here, the sequence f sub n tells you the number of ways you can seat n people in a row, or if you like, the number of ways you can seat n minus 1 people at a circular dinner table. I'm using the symbol f because it has a special name that I'll tell you at the end. It's not Fibonacci, it's something else. First, I want to show you just how to compute the first few terms. So f0, the starting term, is 1. I've already told you that. That's the initial condition. How would I find f1? Well, I can plug n equals 0 into this recurrence relation. If I plug n equals 0, then over here I'll get f1. And over here I'll get 0 plus 1 times f0. Which is 1 times f0, which is 1 times 1, which is 1. Okay, f0 is 1, f1 is 1. The first two terms of this sequence are 1. We might start thinking, shit, maybe they're all 1, but be patient. Let's compute the next guy. If I plug n equals 1 into this recurrence relation, then I'll have f sub 2, right? 1 plus 1 is 2. You have to think of this as being in parentheses. f2 is equal to 1 plus 1 times f1. Well, 1 plus 1 is 2, so this is 2 times f1. f1 was 1, so this is 2 times 1. This guy is 2. f3 is equal to 2 plus 1 times f2. Here I'm plugging n equals 2 into this recurrence relation to get f3 on the left-hand side. And over here, 2 plus 1, n plus 1 times f2. Well, 2 plus 1 is 3. This is 3 times f2. And f2 is 2, so this is 3 times 2. This is 6. I'll do one more. f4 should be 3 plus 1 times f3, which is 4 times f3, which is 4 times 6, which is 24. Does anybody recognize this sequence that goes 1, 1, 2, 6, 24? The next term is 120. The next term after that is 720. It's a very fast growing sequence that has a name, and you may have met it somewhere. If your pre-calculus class discussed the binomial theorem, you should have seen this before. f5, I'll show you. That's 4 plus 1 times f4, which is 5 times f4. f4 is 24, so this is 5 times 24, as promised, is 120. This is called the factorial sequence. Factorials are most naturally defined recursively. Right? That's a nice simple recurrence relation, nice simple initial condition, but there is a way to define it explicitly. Notice what we're doing here. Every time I move up another term, I'm just multiplying by this new input. So, okay, 1 is 1, 2 is 2 times 1, 6 is 3 times 2 times 1, 24 is 4 times 3 times 2 times 1, 120 is 5 times 4 times 3 times 2 times 1. In general here, Fn is n times n minus 1 times n minus 2 times, and you keep going all the way until you get down to 1. There's a special notation for this. We call it n exclamation point. So the factorial sequence can be thought of as being defined by the rule n plus 1 factorial is equal to n plus 1 times n factorial. And this counts, this is the number of possible ways to seat n people at a round table. That's all. The important thing that you remember is this, that n factorial is n times n minus 1 times n minus 2 times down and down and down, all the way to 3 times 2 times 1. And this is the usual definition of the factorial when you want to do some algebra work with it. And one of the things you need to get comfortable with is simplifying factorial expressions. So first, like, suppose I wanted to compute n factorial over n plus 3 factorial. Well, n factorial upstairs is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. Downstairs here, n plus 3 factorial is n plus 3 times n plus 2 times n plus 1 times, and we go all the way down to 3 times 2 times 1. But what's the next term after n plus 1? Well, it's the next term down. That's n. And then n minus 1. And then n minus 2. And what you notice is that within n plus 3 factorial, there is a copy of n factorial. So we're just multiplying all the positive numbers less than or equal to whatever the inside is. If the inside is n, then the factorial of that is the product of all the positive numbers less than or equal to n. If the inside is n plus 3, then the factorial of that is the product of all the positive numbers less than or equal to n plus 3. The n's cancel. The n minus 1's cancel. The n minus 2's cancel. All the shit hiding in these ellipses would cancel all the way down to the 3 times 2 times 1. So this is the same as 1 over n plus 3 times n plus 2 times n plus 1. And one of the things you will need to do in this class is get comfortable simplifying ratios of factorials. Questions on this example or on the definition of the factorial? Okay, then that's where we're going to end it for today. You now have mostly everything you need to complete the homework. There are a handful of theorems that I'm going to show you that will be useful in the homework that you don't have yet. And of course, practice, right? We need to practice quite a bit. So I'll be Friday of this week, I will do some practice problems and I'll show you those remaining theorems for sequences. Yes, Nicholas, my office is still A031D, although we're not allowed to meet there. So for our meeting tomorrow, I'll be hanging out in that office unit. You can come meet me there and then we'll go to a classroom. Because of COVID, the office is so small, they don't like us meeting with students in there. So yeah, meet me in unit 2 downstairs in building A. So go to like walk towards your walking to that office and then I'll meet you in the office unit space there to start. Any other questions here before we sign out for the day? Okay. All right, guys, if you came in late, please watch the video. I spoke for a few minutes at the start of class about some very serious things that I need everybody to hear. So please, I'll have the video up soon. Please make a point of watching it if you came in late. I know a lot of people did. There were only 8 people here when I started. So that is it for today. I will see you guys on Friday. Everybody take care.